Hi, I'm Haotian. Today I will present our work, 3D intuitive physics towards more generalized 3D grounded visual intuitive physics under challenging scenes, which is a joint work with Antonia Torralba, Josh Tenenbaum, Daniel Yamins, Yunzhu, and Tung. Humans have strong intuitions about how a scene can evolve over time under given actions. We also call this intuitive physics, which is a critical ability that allows us to make effective plans to manipulate the scene to achieve desired outcomes without relying on extensive trial and error. As a human, we can learn from a bunch of video inputs from everyday life, which may contain complex dynamics such as fluid, object dynamics, and granular materials. And then we form an intuitive understanding of the 3D dynamics in a given scene. And we can then even generalize it to new scenes in 3D space with objects of different shapes. There are three branches of work on learning intuitive physics. The first branch tries to learn to predict object motions from pixel inputs using frame-centric features. They can generate blur predictions of the 2D feature frames, but it is actually hard to apply these methods to 3D space since they are highly view-dependent. The features will dramatically change when changing the viewpoints. Another branch of work can learn explicit 3D intuitive physics using particle-based representations. Most works require access to full 3D states of the point clouds during the training and testing. However, such information is usually not accessible in real-world settings. Finally, recent work like NeRF proposed to learn view invariant 3D features in 3D space with the help of the Neural Radiance Field. However, they only use the global feature vector to encode the scene, which makes it harder to generalize to scenes with different settings. Here, we propose our framework, 3D intuitive physics, which can learn 3D intuitive physics of complex dynamics from visual inputs only. Our method is composed of a conditional neural radiance field style visual frontend and 3D point-based dynamics prediction backend. For the visual frontend, we train NeRF with condition on input images with only a subset of the videos, using which we can construct the explicit 3D representations of the whole dataset. To get object-centric point clouds, we use color-based segmentation and combined with sparse sampling strategy. Then we train the graph neural network-based dynamics prediction heads to learn the 3D intuitive physics. Since we don't have the correspondence of the point clouds between different frames in the video, we use chamfer loss to train the backend. From the pipeline, we can see that both visual head and dynamics head impose strong relational and structural inductive bias to capture the structure of the underlying environments, which dramatically increase its generalization ability. Here, we generate three multi-view datasets with different settings, including water pouring, fluid cube shaking, and sand pushing. Each of them actually reflect a common interaction with the complex dynamics in the real world. For each of the three environments, we have 6 different camera views and 5 different settings by changing the shape of the container and the amount of the objects in the scene, using which we can test the generalization ability of our algorithm. We show that with the same training settings, our visual frontend shows better results than the baseline 3D-aware methods like NeRF and autoencoder, both in the interpolate and extrapolate settings in the 3 environments. We also show that our learned dynamics module can do long horizon future prediction, outperforming the baseline 3D-based methods NeRF that do not use explicit 3D representation in both interplay and extrapolate setting in the 3 environments we created. Also, we show some qualitative results of the dynamics learner in unseen scenarios of 3D physics systems with fluid, rigid objects, and granular materials. We can see that our methods can learn more reasonable 3D predictions than the baseline methods. Okay, that's all for the presentation. Thanks for listening. And here is the takeaway. More information can be found by scanning the QR code here.